Good morning students. Till now we have studied about what are crystal, what are the different types of crystal, what are the forces acting to hold the atom or ion or a molecule into its lattice points. All those things we studied detailedly in the lesson. Now we are going to learn how these ions or an atoms are packed in a crystal in such a way to maximize the attractive force between them. So if there is a more attractive force, the atom and ions or a molecule will be packed very perfectly. So what are the way to pack these atom and ions perfectly in a crystal? We are going to study that. Now in the packing of crystal, first to explain, all of a sudden if I explain or if someone explain the three-dimensional, it will be very little difficult. So to understand the three-dimensional packing, first they started to explain the arrangement of atom or ion in a one-dimensional way, two-dimensional way. Then they extend into the three-dimensional way. After explaining this packing of crystal, they'll tell you what is the efficiency or the packing efficiency of each crystals. You all know simple cubic crystal, body centered cubic crystal, etc. So let's learn what are the three different types of packing. Like first they are going to tell you about the one-dimensional packing. So only when we come to know about the one-dimensional packing and two-dimensional packing, we will be having a deep idea about the 3D packing. So let's see about the 1D packing. So in 1D packing, how atom or ions or molecules are arranged. So there is only one way we can pack in a one dimensional, because there will be only one direction. I'm drawing that the atom 1, 2, 3, 4, 5, 6. If I take this as origin, consider it as length. Only in 1D I can write the way I can arrange like this. By this you can see that the atom, I am considering this atom is in touch with the two other atoms. So if I ask you the coordination number of this atom, it's said to be 2 because touching with the two neighbor atoms. This is the only simple way. The next let's see about the two-dimensional, how these atoms and molecules are arranged. So in a 2D arrangement, in two-dimensional, these atoms and molecules and the ions are arranged in two different ways. One is called to be AA type, the other one is called to be AB type. One is AA type, the other one is AAA continuously. So the other one is called to be AB type, and it extends. So let's see about in two-dimensional how this atom and molecules or the ions are arranged in a crystal. So I'm just taking this one-dimensional arrangement for this AA. I'm just drawing that, drawing one set of atom like 1, 2, 3, 4, similar size, okay, but I have drawn like this. So A, I'm repeating that. Just below the sphere, I'm going to draw another sphere. 1, 2, 3, 4, 5. Again below that I'm drawing 1, 2, 3, 4 and 5. The way I arrange, so I can take this as a again the same kind, again the same kind, because it's coming one behind the other. All the spheres in this row shows that they are arranged horizontally as well as vertically same. I said it's a two-dimensional because I'm considering this as an origin, so you can take it as length and this can be considered to be a breadth. So it is a 2D arrangement. The way I have arranged one row of element, and it repeats the second row and third row, it repeats the similar arrangement. Now you can find out the center atom or any one atom, what will be the coordination number of this atom. This atom is in touch with how many other atoms? Tell me. This is in touch with this, so I'm considering this 1, and this not touch this, but this is touching this atom, so considering 2, this is touching this 3, and this is touching this atom 4. So the atom in this 2D arrangement of AA type will be in touch with 4 other atoms. So I'm just connecting this 4 other atoms. I'm getting a shape called to be square. So you can call it as a square packing. So in this AA type 2-dimensional, the atoms are arranged in a square packing. If I ask you the coordination number, you can say the coordination number of that is called to be the 4. Now let's see about the AB type packing. What is meant by AB type packing? First I am going to repeat the one-dimensional packing here, that is like A. 1, 2, 3 should touch each other, 4 and 5 I just wrote. And what is that B? B is nothing but the second row atom will come and fill the gap formed between the first row. There is a gap in that. I am going to fill that gap. This is B type. Where in the AA type, where I told you that atoms just below the A, again you are repeating it. But here the second row of atom, I am not writing just below that first atom, I am just filling the gap in between this A type. So I am drawing it. It's going to fill this A type. The depression in the A type. So I am filling it, Now the first row can be designated as A and the second row could be designated as B because it is filling the depression formed between the first layer. And the third row will be again A. A means below, just below this. 1, just below that, 2, just below that, 3, just below that, 4, just below that, 5. So this is A and this is B and this is again A. And the next layer will be B. B will be filling the depression between the upper layer. 1, 2, 3 and 4. So this can be B again. So this type of packing is called as AB type of packing. So I am going to consider the center atom or any one atom. So let me take this atom. Let's find out its coordination number. It's in contact with this one and this will be in touch with 2. This is in touch with 3 and this in 4 and this in 5 and this in 6. So one atom is in touch with the 6 other atoms. So this is seems to be, I'm going to draw that connecting these, seems to be a hexagonal. See that the packing seems to be what? Hexagonal, hexagon. It form a hexagon. So it's a hexagonal packing. You can find it in AB and AB. I'm going to compare AA type and AB type. You can easily say that which type is very closest packing. By looking at the diagram itself, you can say that AB typing is the closest packing. Using this contents, we are going to learn about what is the three-dimensional packing in a crystal. So, three-dimensional packing, I am going to explain how it is packed.